So I'm Fei Wang, and I'm CTO of Alchedata. Today I'm going to give you a very rough primer on what self-evolving physical AI is and how it's relevant to every company that are working on robotics, physical AI here. Yeah. We hear many exciting visions for physical AI. General purpose robots, humanoids, working next to us, machines that can operate almost everywhere, right? But today, I want to make a slightly controversial claim. A robot cannot keep learning after deployment will never become truly general. Most robotic policies still follow a static life cycle. We train them, we deploy them, we freeze their abilities at that moment. But the physical world does not freeze. Object moves, the new edge cases appear every single day. So our goal is a robot, improved after every rollout. When that learn, remember, adapt, and get better through real-world operations. That's the idea behind self-evolving physical AI. Deployment is where the real complexity begins. In training, the world is controlled. Objects are familiar, lighting is stable, the tasks are known. The real world is nothing like that. And it fails in 4 very specific ways. First, long-tail environments. Out in the world, the robots meet the environment and the instructions it has never seen. Second, compounding errors. A slightly inaccurate grasp leads to an unable lift, then a bad trajectory, and finally a failed task. Small errors doesn't stay small. Third, embodiment mismatch. A policy trained on a Franker arm, which is 7-degree freedom, can fail on a UR5. It's 6-degree of freedom. A different camera, different joints, different latency, even though the task is the same. Fourth, the deepest problem, no retrain experience. Without deployment, memory, the robots can meet the same situation tomorrow and fail exactly as it did today, as if it has never seen before. Which is the heart of the problem. Robots train in a fixed world, but they deploy into one that never stays still. And here's why that becomes expensive. Every failure kicks off the same loop: collect, label, train, deploy, test, and round again. We pay for that loop 3 times over. We pay in data collection, robots, people, facilities, annotation, easily tens of thousands of dollars a day. We pay in policy iteration, retrain, reevaluate, redeploy, days or weeks each time. But the largest cost is the one that doesn't show up on my invoice, opportunity cost. Every week inside that loop is a week robots cannot work, the customer cannot go live, and the product cannot scale. The real cost isn't failed action. It's paying again and again for the same lesson. So imagine a different model. What if the robot uses each deployment to improve the next one, right? What if the time between discovering a weakness and fixing it were not days and weeks, but continuous? Every improvement can compound, but only as fast as the loop allows. Think about how a child learns. When a child drops a cup or falls off from a bicycle, we don't erase everything and start from zero. The child keeps what worked, notice what went wrong, and adjust one small step. That's a shift on the slides. On the left, the old way, train, deploy, done, a frozen model. On the right, the new way, a continuous loop where each cycle feeds the next. The robot acts in the world, it remembers better, keeps its trajectory, its failure, its context. It learns and works smarter through diagnosis, improvement, and validation. Then it scales further, carrying that process forward, preserve what works, correct the weak point, and make every interaction improve the next 10. same as a child. Let's open up this loop, right? There's a discipline cycle at the center of our vision, 6 stages. It interacts, the robot acts in the world and collects what happened. Observation, trajectory logs. It evaluates. Was the outcome a success, a partial success, unsafe or just uncertain? It diagnoses not just what happened, but why. It decides how to learn and improve, choosing the right fix for the problem. It updates and evolves, applying that change to the model, the memory, or the skill. And finally, it validates, consolidates, and scales, making sure the new version is genuinely better, hasn't break anything, and then turning one fix into reusable knowledge across tasks and robots. No single box creates self-evolution on its own. It emerges when these stages work together, repeatedly, reliably, and safely. So how does the robot actually improve? Recent research points to 5 complementary ways, and let me explain in detail. First, test time adaptation. Picture a robot lifting a delicate cup and realizing its normal grip is too strong. Instead of retrain the whole model, it adjusts one small component on the spot. And that's TT-VLA, T-square-VLA, TT-VLA, rolled VLA. And by the way, I'm going to share those references at the end. You guys can check in details. Second, imagine experience. Like a pilot practicing a flight simulator, the robot uses a world model to rehearse possible future before spending an expensive physical attempt. And some representative work include rice, water sample, silver. Third, memory and retrieval. Like an experienced technician reaching for a notebook, the robot pulls up a relevant past lesson when a familiar situation appears. And that's retrieve and steer, PEAR. PEAR is our in-house method developed in Alchedata. RoboCortex. Fourth one, program and skill repair. Like a chef fixing a failed recipe, the system finds the broken step, repairs it, saves the improved skill for the next time. And that's Aspire, recently developed by NVIDIA, released in June. 5, at the top, Agentic Orchestration. Here, an AI agent improves not just the robot, but the loop itself, the training code, the data recipe, the experiments, the evaluation. It guides and evolves all 4 of the others. Those aren't rivals. A mature system combines several of them. Now 2 stages in that loop do the heavy lifting, and they are the 2 everyone underestimates. The first is evaluation. Let me get into details on how people actually perform evaluation in self-evolving physical AI. And this is far more than a pass and fail score. It's rule-based verifier, subtask, and progress rewards, learned VLM judges, and confidence and failure detection, even word model-based evaluation. Evaluation is what turns raw experience into learning signal. The second is reflection and failure analysis. This is where the system moves from the task failed to something it actually can act on, localizing which step broken and classifying the failure, attributing the root cause and debugging the traces. Get those 2 right, and you go from the robot failed to the grasp was fine, but the transport trajectory was unstable, which is something you can actually fix. So we built it. Our first policy built on top of Cosmos 3, released by NVIDIA earlier this year. It's a word action model. Improved itself from its own evaluation, from 40% to 40.5% on a RoboLab benchmark without retraining. And let me show you exactly how this is done. And by the way, this is the state-of-the-art result that we are going to report very soon. Then this is our system, self-evolving world models. And the loop is simple. We start by running the Cosmos 3 policy in ESAC lab, where it performs a task and produces a full episode. Instead of recording only success and failure at the end, we collect the richer signals along the way. For example, subtask rewards. And it verifies that applies the environment checks. And then evaluation metrics that summarize the outcome. So we understand not just whether it failed, but where does it fail, where the progress stopped, and which parts of the behavior actually were good that we can reuse. Then two mechanisms turn that evidence into a better policy. First mechanism is test time training. A raise of hand. Have any of you heard of test time training? No? So what it does, you can think of it as adjusting the prompt dynamically, adding a layer so that it can adjust your prompt better, so that robot can actually understand and can actually act on. So test time training lets the policy adapt immediately from its current rollout. No waiting for full offline retrain. The second mechanism is so-called online policy distillation. And this is a very popular concept recently adopted by large language model, or VLMs, to make the student model better. So we are using the similar techniques, and it takes on the strongest successful rollout and treats them as teachers and distill their behavior back into the policy. So the weaker attempts comes up. The approved specialists becomes teachers, and their improvements are distilled into a unified student policy. So the loop is just to run, evaluate carefully, and learn from the best experience, update, and run again. So evaluation stops being a scoreboard at the end. It becomes a teacher that drives the next round. And for those of you confused by the method, then this is how actually it's done. This is on the RoboLab benchmark. The task is to place the white mark at the center of the table. Sounds simple, right? On the left, it's baseline. It fails. And a binary evaluator would throw the whole attempt away. But look closely. The trajectory isn't that bad. It finds the right mark, reaches it, gets a grasp, and starts moving towards a goal. There's real usable progress hidden inside of the failure, right? So we take the more careful approach. We keep the segments that show genuine progress, and we drop the segments that cause the failure. And we update the action interface while keep the backbone stable. On the right, after test time training success. And notice it's also faster. On the right is only 10 seconds, on the left is 30 seconds. The principle is simple. Don't imitate a bad rollout just because it's there, but never waste the good behavior hidden inside it. Learn from the progress, not from the failure. And here's our team. And none of this comes from a single model, right? It takes robotic simulation, data infra evaluation, online learning, all these different techniques put together. And that's the team we've built across the entire stack. I'm joined by our chief scientist advisors, Professor Shuicheng, with H index of 165, and a distinguished professor at the National University of Singapore. Together with a group of researchers who have led work at the top venues in the field. And those are world-class researchers in the physical AI domain. We cover the whole loop, from building the environment and collecting trajectories to diagnosis of weakness and adapting the policy. And this is what we actually shipped over the past few months. Not a roadmap or promises, but a timeline of things that exist. In May, as I introduced, we developed self-evolving world models, turning deployment experience into lightweight policy updates, which is already showing SOTA result. And we are keep improving that. Hopefully we can hit 100 very soon, or close to 100. In June, we built this OpenX Sims and our embodied harness. You can think of it as a one command service across simulators that makes assets commutable between, say, Genesis, Majoko, or Isaac Sim. In July, we built the robot harness and text-to-environment, compiling plain language instructions into measured simulation environment. So constructing simulation environment to test the robots actually becomes much easier. Coming next in August, reference-based text-to-environment. What does that mean? You can not only use natural language, but also combine with, say, a snap of photo or short video of your environment. And you can turn it in a testing environment that you can test your robot in, right? And we're also going to release Pearl, a self-improving agent for physical AI. All of this reflects one shift in mindset. We stopped asking, how do we train a policy once? And start asking, how do we build a system that keeps growing the policy? And that's our goal. So where does this go? The world is too big to memorize, as we all know. No robot can pre-learn everything, every home, every factory, every road, every object or failure mode. It has to learn from the experience after deployment. Second, the robot becomes a continual learner. As our friends at RoboLab or Recursive are trying to build, right? Not a frozen model, something that can observe, adapts, remembers, and improves, even on a limited compute. Third, self-evolution becomes recursive. The AI improves not only the policy, but the data recipe, the simulator, the evaluation, the training code, the whole loop. Last but not least, the safety is the gate. Every improvement must pass evaluation before it reaches the real world. Self-evolving does not mean uncontrolled learning, it means verified learning. Because of the future of physical AI is not the bigger models or bigger brain. It's a robot that gets better every time it meets the real world. With that, I want to thank you, and I also welcome you to join this journey of making the robots become smarter and become self-evolving. Thanks all. And here are the papers. And if you guys are interested, our booth is outside, just showing demos, posters, all the components that I shared earlier. Yeah. Thanks all.